Good morning, everyone. As Marco mentioned, my name is Nick Martin. I am a content engineer here at Markforged. And today we're going to be talking about some of our favorite composite 3D printing applications of 2018. There we go. So here's a little overview of what we'll be going over. We're going to talk about some end-use robotic parts, some inspection fixtures, customized work holding, mold tooling, and some engineering education stuff. And each customer example is going to offer a look into how Markforged has expanded the uses of 3D printing in the entirety of the manufacturing cycle. So whether it's functional prototyping, tooling and fixturing, all the way to end-use parts. And so our printers really expand the part capabilities of what you can 3D print and speed up that time to market and reduce costs. So we're going to look at some examples of that today. So first, let's talk robots. Haddington Dynamics is a company that uses a Mark II, and this is actually one of my favorite applications of our printers. Basically, one of their founders has a background in supercomputing, and they wanted to utilize that background to make an easily trainable, really accurate open source robotic arm. And so this is going to require parts that are both really low weight and also have a really high stiffness. And so this on the slide is a screenshot of the CAD of the open source robot that they make called Dexter. And you can actually, this is a screenshot directly from their website. And so to increase the manufacturability of this arm, while really remaining committed to that open source philosophy, they decided that they were going to 3D print the majority of the arm. And so here's a picture of a 3D printed part from one of the original arms that they made for one of the first versions of the robot. And it was a really great option because it made this robot more accessible. Anyone with a 3D printer could print these parts and made it a lot easier to manufacture as well. But it raises one issue. So as I mentioned, this robot would require a really high stiffness because it's designed to be a precision machine. And they printed these parts out of PLA. This orange part is out of PLA, which is one of the most common 3D printing plastics, but they found that it wasn't nearly strong enough for their needs. So right here, this is a little popsicle stick that's printed out of PLA. And you can see that you can just snap it into very easily. And so that wasn't working out well enough for them. So what they decided to do was hand reinforce these PLA parts with carbon fiber. So they would order these carbon fiber pieces and leave spaces in the parts in their design for these to be inserted after the print. And they found that this actually did give the robot adequate strength, but it resulted in a really clunky 800 part design. And so this assembly, as you can imagine, took days, about a week actually, to assemble these 800 parts. So they decided to purchase a Mark II, which is our desktop series composite printer. And so with the ability to reinforce these parts with continuous carbon fiber, they were able to simplify the design and have parts ready for use right off the print bed. And so the reason they were able to do this is because continuous carbon fiber has a strength to weight ratio that's higher than aluminum. And so these composite parts could meet their stiffness and strength needs while remaining extremely light. So I have some examples with me. So this right here is an example of a pulley that they printed on a Markforged printer. And here's a coupling right here. And these parts are all reinforced with continuous carbon fiber. And I have a bunch of them here with me that I just printed these a couple weeks ago. And here, I don't know if you can see, if it's zoomed in enough to see this, but this shows the routing of the carbon fiber on the inside. And so this is one of the couplings. And you might be able to see there that shininess on the inside is that continuous carbon fiber. And so what this allows is this is a popsicle stick with the same dimensions as that PLA stick. And I can bend this as hard as I want. I've been passing this around the office to see if anyone's able to break it, and no one has yet. But this, you can see I'm really cranking on it, and there is barely any deflection. And so this continuous carbon fiber gave them the performance of when they were actually hand inserting these carbon fiber pieces into it. And what this allows them to do is have a robot, that has repeatability of 30 microns, which is about 1,000th of an inch in 3D space, which is just unbelievable. And so here's a video that I can show you. And in this video, you can see that he has these two robots, and one of them, he is training. The robot on the left of that video, he is training by moving it around with his hands. And the robot on the right is following the movements that he is directing it. And so what's going to happen is he's going to finish training this robot through this movement. He's going to keep doing it all the way till he's done. And then what he can do is play back what he just trained the robot to do. So this is super useful for pick and place machines, CNC, other manufacturing, to have the ability to have this really high repeatability in a robot that you can train with your hands. You don't need to know a coding language to be able to do this. And so you see that this robot is mimicking what he had just trained it to do. And it can take up to a 3 kilogram payload with that 30 micron accuracy in 3D space. You should check out their website. They have a lot of really cool videos like this that show off their capabilities. And this robot, as I mentioned, is almost completely printed out of our carbon fiber reinforced parts. And so last note on Haddington, in addition to like really leveraging this rigidity, they can print like super complex parts. They print their own optical encoders, and their cycloidal drives, which is just the transmission of this robot, is almost completely printed out of our parts as well.
So actually, let me just pitch in here really quickly. If anyone wants to see one of these robots, if you have the opportunity to go to CES, we will have a booth there, a Markforged booth, and we're going to bring one of these with us to the booth.
Yeah, you should definitely stop by. I'll be there. Clyde will be there. We'll have a robot arm there. So you can come check us out. All right. All right, so next up, we're going to talk about a company called Lean Machine. And so they're a metal fabrication company, and they utilize a 5-axis CNC mill. And this performs different metal fabrication processes. And one of their projects entails taking really long pieces of extrusion and machining the ends of it. And so this stock, as you can imagine, has to be secured in multiple places to keep it rigid and in place when they machine it. And so what they did, this is a rendering of their setup. You can see that they have a bunch of off-the-shelf vices lined up. And what they do is they secure this really long stock in those vices. And they're shown in gray and blue in this rendering. And it keeps that piece. It's really important to keep work rigid when you're cutting it, because it can start vibrating or deflecting, which decreases your accuracy, can cause chatter, and give you a really crappy surface finish. And so what they do is they clamp it in multiple spots with these vices. But what they found is, due to the large profile of this 5-axis mill, you can see the head of it in that slide. It was really hard to position the vise near the end of the stock without causing it to collide with the mill heart, causing it to collide with the vise during cutting. And so they were really left with two options. The first is to use off-the-shelf vices, as they're doing, to clamp the extrusion as close to the end as they could, which would leave a large portion cantilevered off the end, and which would sacrifice the speed at which they could cut and the quality at which they can cut. You can imagine if you like stick a ruler off of the end of a table and you poke it, it deflects a lot and vibrates. And so that's what they want to avoid. So that's not really a great option. Secondly, they could create their own custom vices, which would allow them to create one with a smaller profile so they can actually clamp it on the end of the stock to keep it from having that cantilever action. But machining a new vise is pretty counterproductive, considering the fact that it would take them as much time and manpower to design and machine as it would to do the actual project. So that didn't make much sense. But when they received their Mark II, they found that continuous fiber reinforcement provided stiffness and strength that was high enough to print parts for a custom vise. And so this offered them a viable way to fabricate the vise because you don't have to do any cam and it can print overnight without any supervision. So they catted it up. This is a rendering of the vise that they started to create. Every part in black is printed on one of our printers. There's about 24 3D printed parts in this vise. And then they threw it in Eiger, which is our slicing software. Some of you may have heard of it before. And here they were able to select exactly how and where to reinforce these 3D printed parts with fibers to withstand the clamping forces during operation. And so you can see the blue parts in it are, in those Eiger screenshots, are where fiber is being routed. You can see right here. And then they threw it on the printer. So this is a photo being taken as the parts are being printed. This is from an angle above the print bed. And you can see the black is Onyx, which is our thermoplastic material. And then that white is fiberglass. It's continuous fiberglass strands that it's being reinforced with. And this is what the vise looks like fully assembled. And it's positioned next to one of the off-the-shelf Kurt vises that they are using for the rest of the clamping. And as you can see, the right side of the Markforged printed vise is a lot less meaty than the right side of those Kurt vises, which is the whole idea of making this custom vise, to allow that mill to come in from the right side and make that cut without interfering with the vise. You'll also notice they practice really good design for additive manufacturing. They integrated off-the-shelf hardware where they could instead of printing it, which is always a really good practice. And so let's check out a video of it in action. So here it's making its first cut on the end of this stock. And it extends to the left very, very far. You'll see once it turns around, you'll be able to see down to the other end. So this mill makes its first cut, and then it turns. And I'll pause the video really quickly right here. So you can see that this stock extends really, really far up to screen right. And you can see all the Kurt vises that are clamping the stock. And then on the bottom of the screen is their custom vise. And what you're going to see here is as the mill comes in to make its second cut, it can get really close to the end of this piece of stock so that it can make that cut without that end being cantilevered off. So here it comes in, and you'll see on the right side, it's getting really, really close to where that vise is. This is where this custom vise is really helpful. And they're able to make these really quick, really accurate cuts. So printing custom vises allowed them to have secure clamping of the workpiece closer to the area being cut, which increases the speed at which they can cut the stock and increases the accuracy and surface finish quality of the extrusion. In addition, because the vise is printed with soft jaws rather than steel or aluminum on the actual piece interfacing with the part, this reduces vibrations from the tool, which it damps those vibrations, which even further increases the quality of the cut. So next up is an example from Humanetics, who is the leading manufacturer of crash test dummies. If you, oh, sorry, my bad. If you tuned into my webinar last week, you've heard a bit about them already. So they utilize Markforged printers throughout their process. They fabricate everything from tooling to fixtures to end-use parts. For example, we have Clyde here. Oh, he's heavy. So the skeleton of Clyde is printed out of Markforged parts. Every black part that you see here, his ribs, his arms, hands, his legs and feet that you can see there. And a lot of their parts they reinforce with Kevlar to give it some realistic strength for the dummy. And this is Clyde, as we introduced him earlier, and they were kind enough to give us Clyde so we can show people. But maybe I'll have him join me on the rest of my webinars too. Oh, all right. Anyways, so the part we're focusing on today is not Clyde, although we love him very much. What we're going to talk about is the neck ring. So this part is really crucial in protecting the electronics of the dummies. So during a crash, they want to make sure that no debris or anything gets in through the hole that occurs around the neck area. And so they have this really complex shaped neck ring. As you can tell probably from the picture, this isn't a 3D printed part. It's fabricated in a thermoset mold, meaning the material is injected into a heated mold to get the desired geometry. So before Markforged, they made these molds out of silicone, which did the job, but wore out quickly and had to be remade. They considered having one machined out of aluminum, but this would cost thousands of dollars and take weeks, if not months, to receive. So what they did is they purchased an industrial Markforged printer, the X7, and then engineers at Humanetics tried 3D printing the molds. So I have one with me today. And so it's a two-piece mold. And if you look inside, you can see that neck ring shape. And it's pretty complex. This mold is tilted at this angle. And we were able to print it into a two-piece mold that, oh, wrong way, fits together like this. And so Onyx, which is our thermoplastic, is able to give it a really, really nice surface finish all over this part. And they reinforced it with HSHT, which is our high strength, high temperature fiberglass. And that helps the mold retain its shape during the heating and clamping process of making the actual part. And this mold ended up far outlasting the silicone mold and was 99% less expensive than if they were to machine it out of aluminum, because this would most likely have to be a multi-part mold if it were made out of aluminum. All right, so next up, we're going to talk about J.J. Churchill. So they're a manufacturer of jet engine components. And one of their parts is a turbine that has specs with really, really tight tolerances. So because of these strict dimensioning requirements, the turbines are inspected closely with something called a coordinate measuring machine, or a CMM for short. And so you can see the end effector of the CMM in this picture on the slide. And basically the machine knows the precise location of its end effector, and therefore it can make really accurate measurements of the part as it touches multiple points on its surface. So during this process, it's critical that the turbine not move or deflect. This is typically achieved through a custom aluminum CMM fixture that the part is clamped into. But as you may guess, based on the theme of this presentation so far, custom machining the fixtures is expensive and time consuming. It costs them about $2,000 per fixture and had a lead time of about 2 weeks. So they decided to 3D print it. Typical 3D printing materials would not stand a chance at holding this turbine in place. But when they reinforced it with carbon fiber, this part, which printed on a Mark II, was stiff and strong enough to replace aluminum for 80% less money and in 70% less time. Another added benefit of printing this part is, as I mentioned earlier with the lean machine example, is Onyx is non-marring, meaning that if you clamp a metal part with Onyx, it's not going to deform or scratch the surface of that metal. And this is really important in fixturing for inspection, because you're trying to see if the part is to spec. And if you're marring the part during that and ruining the part, it defeats the whole purpose. And before, they found, J.J. Churchill found that when clamping it into the aluminum, sometimes they deformed the part or scratched the part and had to completely toss it, and it wasn't even working. So they found that when they 3D printed it, they never marred the part, and they actually got higher yield on their manufacturing during the inspection process. So our last customer example is from a high school, actually. The first robotics team at Hunter College High School uses a Mark II to print parts for their robot that they use in competition. Continuous carbon fiber reinforcement allow them to 3D print the parts for their drive system. And these are all the parts in their drive system included in this picture. And here's a picture of it assembled. This is what's called an omnidirectional drive, meaning that it allows the robot to drive in any direction independent of the way that it's facing. And the students reinforced the parts with continuous carbon fiber, which allowed them to 3D print pieces of the drive they would otherwise have to machine. And I really like this example because it's not, we give a lot of examples of companies saving time, saving money, getting to market faster, which is all good and great. But this is an example of just allowing easier access to engineering education to a high school through more advanced tools in 3D printing, which is a really cool thing to see. And so that was our last application. I hope that you see whether it's parts that are high-performing end-use parts, whether you're trying to save money during the manufacturing process or educate budding engineers. Markforged printers unlock tons of new applications for additive manufacturing. And hopefully you gain some insight into how 3D printing with composites could help your product development process. And so now we're going to open it up to questions from you all.
Yep. So you should see within your Zoom interface, 2 windows. You can pick either one. We'll be looking at both. One is the Q&A window where you can type in your questions, or just in the chat window. Both work well. If you'd like to see more applications, you can visit us at MarkForcecom. We have an applications page with plenty more applications, both regarding tooling and fixtures, but also in all the other categories in which we have applications for this kind of printing technology, including prototyping, end-use parts, specific things like welding fixtures, etc. If you want to learn more about the printers or materials, there are also data sheets available on the website, which can give you more specifics and numbers if you have a specific thing in mind. For example, if you're looking for like the heat deflection temperature of Onyx, things like that, all of that is available in data sheets on the website. And I think, Nick, that we have some questions coming in right now.
Great. So let's see. First question's from Peter. Regarding the Vise parts, are 3D printed threads robust enough to handle direct connection to the threaded rod, or are metal inserts required? This is a good question. So our printers are capable of printing effective threads, but when it comes to something like a Vise where you don't want any backlash at all, I would definitely recommend using hardware, and that is what they did. And there's a lot of different ways to insert threads into a part. Whether you're doing a heat set insert, you can place it during the printing process. But this goes into the whole idea of design for additive manufacturing, where you're pairing 3D printing with good engineering practice to make robust parts. So to answer your question, some instances, printing threads is good. A lot of the time, using hardware is more robust. A question on how expensive materials are. So this information you can find on our website. Also, this is an interesting comparison. It's a little apples to oranges because a material like PLA or ABS, you're printing the entire part out of that thermoplastic, whereas our continuous fibers, you're only reinforcing a section of the part. You may only do a sandwich panel or something like that. And so those fibers, they run more expensive. For example, off the top of my head, 50 cubic centimeters of carbon fiber is around $120 or something like that. But you keep in mind that you're not using that throughout the entire part. You're reinforcing it in specific areas. Question from Kevin. What about parts that are dealing with heat? How effective would that be? This is a good question, more of a materials-based question. So Onyx, which is our thermoplastic, which is present in every composite part, has a heat deflection temperature of 145 degrees Celsius, which is around 300 degrees Fahrenheit. And if you want to reinforce that part, like in our thermoset mold, you can do that with our high temperature fiberglass, which has a heat deflection temperature of around 150 C. And so operating at those temperatures is no problem for those materials. Let's see.
I see that someone's asking about sample parts, or can you make sample parts that we can hold to understand print quality? If you would like a sample part, you can request one at MarkForcecom. There's not on the homepage right now because we're doing an H13 launch, but there's a button where you can actually click through to fill out a form, and we are going to send you an Onyx part that's been reinforced with carbon fiber, as well as a standard nylon part, so you can actually make a comparison and see for yourself how strong that is. And that's actually the part that Nick was holding up earlier. It's this little keychain here. So if you want a copy of that, or if you want one of those, just fill out the form and we will send it out to you.
Yeah, I also see there's some questions coming through the chat window. If you could direct all of your questions to the Q&A window, that will be helpful so I can streamline them all to one area. One question asking about, let's see. Can you embed hardware during a print? Yes, you can embed hardware during a print. You can actually schedule a pause in the print in Eiger, our software, very easily, and it will pause on that layer. You could even take the bed out, embed your hardware, put the bed back in with very high accuracy, and then press resume, and your print will continue. A question about comparing aluminum and Onyx when it comes to impact and durability when it comes to indentation. That's from Charles. That's another good question. So when we compare to aluminum, we're not talking strictly about Onyx. So Onyx is our thermoplastic mixed with chopped carbon fiber. When you reinforce that with continuous carbon fiber, that's when you really get that aluminum strength. And compared to aluminum, I would encourage you to check out our data sheet to find out the specifics you may be looking for there. When it comes to impact resistance, high strength, high temperature fiberglass is a really good fiber for that compared to carbon fiber. As you may know, carbon fiber is more of a brittle material, although it's high strength. Its resistance isn't as high. A lot of soft jaws that our customers make are either reinforced with Kevlar or fiberglass. Let's see.
I see someone's asking whether we're going to be emailing out the recording to share with coworkers. Yes, we will be. So we've been recording today's webinar, and it takes us about a day or so to process the recording and upload it to the website. But as soon as we do that, we're going to send you an email with a link to the recording. If you don't get the email, or if you want to find it again, if you visit us at markforged.com/videos, you can actually see a repository of all of our previous webinars.
All right, so a question from Scott. Aside from threaded inserts, which are heat set into the part post-print, are there examples of hardware you've seen used? Yes, tons of examples. One of our customers, Centerline Engineering Solutions, they use steel inserts on a punch and die that they print with our composites. There's examples in the Haddington robot where they push hardware into their pieces. There's a ton of examples. It's as I mentioned, good additive manufacturing practice is using hardware as you would in any other part that you may machine, and really combine that with your 3D printing. All right, question on any high temp applications for your material above 500 degrees Fahrenheit. So this would really depend on the application. I would need a little more detail to fully answer that. But we definitely have applications where that are temperatures upwards to that our parts are being used. For example, sorry, I just lost my train of thought. Oh, in welding fixtures, obviously the end of a MIG welder reaches temperatures much higher than 500 degrees Fahrenheit. But although the heat deflection temperature of the materials, our high temp materials, is around 300 Fahrenheit, they can still be used for welding fixtures because that 500 degrees Fahrenheit is not directly being applied to the part for the entirety of its use. So depending on how that temperature is being used or affecting the part, yes, it can be used for high temp applications like that. A question on the temperatures and pressures used in the neck ring mold. I'm not sure on the exact numbers on that, but I can find that out and we can add that to our case study, which is online.
Karsten is asking, do you have any material which is qualified for food context so that it can be used in the food industry? We do not at the time. We really don't suggest that you use our Onyx material in contact with any food, just not something we really tested or were certified for. However, if you have an application where you're producing something on a manufacturing line where you need to use or you need to 3D print some sort of work holding, which will not be coming into direct contact with food, or you're in a situation where you can print something that does not need to be certified because it's not coming into any direct contact with food, there's a lot of kind of auxiliary applications that are useful. And this also applies for other industries where certifications are required that we don't have. For example, in certain aerospace applications, our materials are not at the time flight rated. However, there are plenty of applications we found in aerospace where there's some sort of production process in which work holding or tooling and fixturing is helpful or can be 3D printed that is not actually being put on a plane. And in those situations, the materials and the printers are a perfect application.
Great. Let's see. Question from Peter: does the machine use a separate support material? No, our software lays out support material in Onyx that's easy to just remove by hand after the print is finished. A question on the yield strength of the Onyx material from Nathan. So you can see this on our data sheet. Onyx is a thermoplastic, so the yield strength of Onyx is not that compelling. It's, it has a strength that's higher than most other 3D printing thermoplastics. But what is exciting is when you reinforce that with fibers. So for example, if you were to reinforce it with carbon fiber, the strength of that part would be 20% higher than the yield strength of 6061 aluminum. All right, let's see. Leonard has a question on the maximum size our printer is able to handle or print. So this depends on the printer you're talking about. So our desktop series has a print volume of about 6 inches by about 13 inches by maybe 6 inches, and then, or 8 inches, I think. And then our industrial series, like the X7, is about twice that build volume. And you can find all that information online. Any recommendation on plating Onyx parts, nickel, chrome, or other similar plating that you can suggest? I'm not an expert on plating Onyx parts, but I have a couple coworkers who have nickel-plated Onyx, and there's a couple parts laying around the office. So yes, it's possible, but I can't talk too much about it because I personally have not done it yet. A question on, are printers capable of printing higher performance polymers like PEEK apart from just composites? The answer to that is no. Our materials are part of our IP and are specific to our printers. So the materials that we currently make and sell are the only ones that you print on our printers. A question on speaking to the machinability of the Onyx outer surface for precision interfaces. Does disrupting the continuous nature of the Onyx strands disrupt the strength of the part? All right, so a couple things with this. Again, this is sometimes a misconception that I like to clear up. Onyx is our thermoplastic that has chopped carbon fibers in it. So there are no continuous fibers in Onyx. You reinforce that with our continuous fiber that's printed by a different head. And so that's number one. Number two, I would advise against machining Onyx for a couple reasons. Number one, if the purpose of machining it is for surface precision, our industrial printers can print with a precision of around 50 microns, which is less than 5/1000th of an inch, which often is comparable to machining it already. Secondly, thermoplastics are notoriously terrible at being machined. It offers actually a worse surface finish than if you were to actually just print the part.
So actually, I'd like to make another note about materials because what happens is people often request specific materials that have specific properties for their applications. And this is in reference to the food question earlier, but also a lot of the other questions about materials. One of the things that we recommend is that when you're implementing additive manufacturing in your facility, and when you're kind of walking the line, which is what we call this process, when you're kind of going through your manufacturing operations and taking a look at all the places where additive manufacturing can be implemented to help you out, whether it's to cut costs or improve your ability to iterate on your manufacturing facility, there are situations where you might need a very specific material to come into contact with another, with a part. For example, in some work holding application, maybe you really need, aluminum to be the part that's coming into contact with whatever you're holding. There are situations like that where you can actually implement additive manufacturing by 3D printing not the contact surface, but the rest of that work holding, and then only having a contact pad out of the material that you need. And that way you can get the cost savings and you can get the ability to iterate on the rest of the work holding really, really quickly while still achieving the precise contact material that you need.
Yeah, and that's a very great point. An example of this is Dixon Valve, which is one of our really big customers. And they print end effectors. And if you print an end effector out of composites or thermoplastics, it's obviously going to be a lot lighter, which allows you to move the end effector around more quickly and can increase your production. But the issue is that the surface of a thermoplastic or a composite is going to wear quicker than steel. And so what you can do is add steel inserts to the edge of that end effector. And what that does is it makes a really wear resistant yet lightweight end effector, because most of it is printed out of thermoplastic and composite, and then only your contact surface is that really tough wear resistant material. I think that is all of the questions that we have today.
Mm-hmm. It looks like it. Yep. So just to kind of close out here, again, we're constantly working on our website, MarkForged.com. You'll see it evolving all the time. Right now, if you go to MarkForged.com, you'll actually see where we've put up H13 tool steel as being now available, which is kind of an exciting piece of recent news for our Metal X printer. We are, as of Tuesday, so as of just a couple of days ago, we've released H13 tool steel. So if you're interested in printing metal, know that you can now 3D print not just 17.4 stainless steel, but also H13 tool steel on our Metal X. But then also, if you go to the website and you go to the top bar, you'll see sections on our products where you can get detailed information on specific printers, and that includes spec sheets for build volumes, tolerances, precision, things like that. There's a materials section, which has just actually been recently revamped. There you can also find data sheets for both our composites and our metals. The applications page is very relevant to what we talked about today. There you'll see a wealth of different applications. We have all kinds of webinars and case studies for various applications in which our composite and metal technologies make a big impact. We have a learn section where you can actually read up in detail about some of the processes involved, how the software works, how the materials work, etc. And then the final thing I'd recommend is if you would like to try out actually reinforcing some parts yourself. So let's say you have a CAD part in mind, and you're curious about what it would look like reinforced. That is, how long it would take to print, what the material cost would be even. You can actually basically simulate that yourself by signing into Eiger. That's on our website in the top right. And Eiger is, Nick touched upon this earlier in the presentation, is our slicing software. And if you go to that page, you can actually sign in to a trial account. So you don't actually need a printer to get started here. And you can log in and you can upload your own parts, and you can actually reinforce them to your desired configuration, and Eiger will tell you print time estimates, it'll tell you cost estimates, and you can actually see what that part would print like. So you can actually kind of simulate, through your parts reinforced, just to get a feel for what you can do with the technology. And with that, I think we're going to close things out. If you have additional questions, you can get in touch with us on the website as well. We have been recording today's webinar. We're going to be distributing the recording to you as well, so look out for that in your inboxes. We'd like to thank you so much for joining us for today's presentation. You've been a very engaged audience. We love reading your questions and getting your input during the presentation, and we hope to see you at the next one. Thank you so much and have a great rest of your day.